Alright, on to part 2. Whoops. Got it. Alright, so water is flowing into a tank. The depth in feet of the water at time t in hours is h of t. Interpret with units the following statements. H of 5 is 3, h prime of 5 is 0.7, h inverse of 5 is 7, h inverse prime of 5 is 1.2. So I want you to interpret those 5 statements in the context of the problem and then with the units. So I'm going to do the first one with you because it's the easy one and that makes things easy for me. So h of 5 equals 3. Well, this is height at a given time. So what is this saying? This is saying after 5 hours the depth is 3 feet. So t is 5, h of 5 is 3, after 5 hours the depth is 3 feet. So I want you to interpret B, C, and D just like that. Pause the video, unpause when you're ready to check your work. Okay, so now let's look at dh dt, or h prime of t, is the rate of change of height at time t. So h prime of 5 equals 0.7 is saying at 5 hours time the depth is increasing at 0.7 feet per hour. So that's the instantaneous rate of change at 5 hours time. H inverse of 5 equals 7. Well, what is H inverse? Remember that a function in its inverse, you're literally switching the variables. So I say switch x and y, but we're really switching h and t. So h inverse of t is actually the function t of h. So this is a function time with respect to height. So h inverse of 5 equals 7 is saying when the depth is 5 feet, it has been 7 hours. H inverse prime of 5 equals 1.2. Well, if h inverse of t is actually t of h, then h inverse prime of h is actually dt dh. So it's the change in time with respect to the height. So it's a little bit confusing to phrase this, but should make sense. So 5 is still representing a depth or a height. So at 5 feet depth, it takes 1.2 hours to increase a foot in depth. So basically it's 1.2 hours per foot is the rate, or the instantaneous rate of change at 5 feet in depth. Good stuff. Again, this is all really important to make sure it gives you a really good understanding of actually the relationship between a function and its derivative, in this case also between a function and its inverse and the derivative of its inverse. But it's one thing to be able to go through the process of, the power rule, the product rule, the quotient rule, and just find a derivative and work it out. It's another thing to actually understand what is that you just found. So that's why you're going to see a lot of these types of questions on the notes, as well as on reviews and tests and quizzes, as well as things like this next problem, which we've done a lot of examples like this already. So here, if I give you a graph of a function, so this is the function f, I want you to sketch f double prime. So sketch the second derivative. I would recommend sketching the first derivative first to find the second derivative. So I want you to pause the video and sketch the second derivative. Unpause when you're ready to check your work. Okay, so the second derivative should look something like this. It should be a line, and it should have a y-intercept somewhere right around this point. Yours might be a little bit to the left or right, but it should be somewhere around there. And it should be increasing the entire time, and it should be positive to the right of this point and negative to the left of this point, which would make it increasing. So how do we come up with that? Well, alright, first let's look at the first derivative. Well, I know when the function has a maximum or a minimum, the first derivative is going to be at 0. When the function is decreasing, so from the maximum to the minimum, the first derivative is going to be negative. When the function is increasing, the first derivative is going to be positive. When it's increasing, the first derivative is positive. Okay, so now I'm basically using those same ideas to find the second derivative. So when the second derivative, or when the first derivative has a maximum or minimum, the second derivative is going to have a 0. When the first derivative is increasing, the second derivative is going to be positive. When the first derivative is decreasing, the second derivative is going to be negative. Now we will learn some other relationships between a function, its derivative, its second derivative, and the graphs in the next unit, so we'll be able to get a little better idea on some of the other details. But for now, it's basically just being able to get a general sketch of what's going on from the information you have. Do I know for sure that it's going to look exactly like this? No, I don't know for sure, but I know that those key features that I pointed out have to be correct. Alright, so higher order derivatives are just derivatives of the derivatives of a function. Great. Our main example that I talked about before, but now I'm just going to bring up again, is that if we have s of t as a position at time t, then v of t is the derivative of s of t, which is s prime of t. That would be the velocity. It is a rate of change of position at times t. A of t, which is the acceleration, is the derivative of the velocity, which is the second derivative of the position. So that's the acceleration, which is a rate of change of velocity at time t. And as you saw from our height and depth example, you know, it doesn't have to be just position, or in that case I guess that was position, but we can also look at inverses and a lot of other relationships. So this is just one example of a relationship between a function and its first and second derivative.